Okay, very good. Let's start going to second order numerical flux. Okay, so that from here, we are going to go away from our piecewise constant assumption. Okay, remember we are storing the volume averages across the volumes. So if the volume average is here, it doesn't mean I have to use a piecewise constant approximation to approximate this. For example, I can use a linear approximation as long as the center of the linear approximation coincides with the volume average. This is a piecewise linear approximation that is going to give me exactly the same volume average as stored by my computer in a finite volume scheme. So if my function is like this, if my piecewise average look like this, maybe I can construct an approximation that looks like that. It is still discontinuous across the volume boundaries, but if I construct the piecewise linear approximation in a good way, I can get better approximation than the piecewise linear one. And that is the idea behind the second order numerical flux. The second order numerical flux is not actually a different numerical flux. It's a different way of approximating the function using only the average information, using only the piecewise averages. Okay, the trick is, how do I reconstruct the value of the function on the left and on the right of this interface? As long as I can do that reconstruction, I can keep using good enough flux, right? Because if I still zoom into that region, if I zoom in very, very closely, it still looks like a Riemann problem. On the left of the discontinuity, it looks like this value. On the right of the discontinuity, it looks like that value. I can use exactly the same method we discussed just now. I can use exactly the same code, actually. All right. And previously, we had a question that we don't want to take information across the shockwave, right? And if we treat every interface as a potential shockwave, then we want to use only the left of the discontinuity to reconstruct this value. And we only want to use the right of the discontinuity to reconstruct that value. Is that right? So a simple method is extrapolation. We have the volume average here, we have the volume average here. So why not we extrapolate for this value here? Okay. So first of all, to do that extrapolation, we need to convince that like we are doing a proper second order reconstruction, because all of these complexity is trying to go away from first order going to second order. And first, let's convince us that the value at the center of the cell can be approximated to second order as the average value in the cell. In other words, U at xi, where xi is the center of the cell. Remember, these interfaces are xi plus half, can be approximated as ui bar plus O of delta x squared. Okay, and how do we convince us this? We can remember u of x can be represented as u of xi next term. Yeah, du dx at xi times x minus xi, right? there is no delta x anymore because I'm looking at the value of x actually within the cell. This is because I want ux because the volume average involves ux. Okay, what's next is half of d square u dx square, also at xi, times what? X minus xi square, and then plus O delta x cube, right? O delta x cube, because if I'm looking within each cell, then x minus xi is going to be less than delta x. All right? Okay, so now let's look at what the volume average is. The volume average is 1 over delta x of the integral ui minus, not ui, xi minus half and xi plus half of ux dx. Oops, where I am. Okay, and now if we integrate this value, we are going to get the first term is constant. It doesn't depend on x, right? The first term we get, this goes into simply 1 over delta x of integrating a constant dx times, because the constant can be moved out, ui bar. And this is just a 1, right? This is just 1. The second term is even more interesting. So I'm going to be integrating from xi minus half to xi plus half, x minus xi dx times a derivative term. And I'm going to convince you that this term is equal to 0. Because xi is, I mean, in one-dimensional case, it's even more obvious. But in general, this term is the integral of x minus xi over volume. And as long as xi is the centroid of the volume, that integral is 0. As long as xi is the center of mass of that control volume, an integrand like this is going to be 0. So the derivative term goes away. Okay, so this goes away. And then whatever is left, okay, whatever is going to be left is O delta x square. So this term is already O delta x square. It doesn't matter if you integrate it over a small volume and divide by the size of the volume. It is going to be O delta x square. So plus O delta x square. All right. So what I'm doing here is convincing you that the volume average, which we have in the finite volume scheme, is a second order approximation of the cell center values. The cell center values are just the center of the interval in 1D. But in general, this is true even we go to 2D or 3D. Even if we have a crazily shaped control volume, that is also true. Whenever you have the centroid of the volume, the value at the centroid is a second order, can be approximated to second order by the cell average itself. All right, that is a very convenient truth that we can use in second order finite volume methods. Okay, good. So now we know we have a second order approximation of the value here. We have a second order approximation of the value here. We want to extrapolate the value here to second order. Second order approximation is basically a linear approximation. We can draw a straight line here and, okay, get the value here, right? If we have a uniform grid, that's extraordinarily easy. Even if we don't have a uniform grid, we can just link these two cell centers and find the slope. And the slope is an approximation of the local derivative. And the local derivatives can be used to extrapolate the solution here. So, in other words, u of I plus 1 plus half left. Okay, so left because at this point I have two values, one from reconstruction from the left, one from reconstruction from the right. Remember, there is a discontinuity, so I need two values. The one from the left is equal to u of I, which is the value here. And this, actually, I'm going to write approximate here because this is just a second order approximation. Ui plus half of delta x. So this is half of delta x times the derivative of the or the slope here. The slope is ui minus ui minus one. Yeah. So this is the this is ui minus 1 divided by delta x. Delta x is the distance between these. Yeah. Right. So this is a good second order approximation of the left value here. And ui plus 1 plus half right can also be approximated by this and these values. It is ui plus 1 now minus half of delta x times ui plus 2 minus ui plus 1 over delta x. So this is the slope from the right. Now it's interesting, we have a second order scheme here, and we are using values way from the left and way from the right. Do we want to try plug into our code to see how that performs?